Okay, let's get started. So, welcome back. Uh, Today will probably the last, if not the next to last course. So, I didn't have any precise subject in mind for the next course, which is actually still available. I don't know if it's officially vacation for the master student next week. Next week, it's no course for master students. Still there's class? Okay. So maybe there will be kind of a small last course, maybe 1 hour just to kind of wrap up the whole thing. But in principle, I should finish today with what I wanted to say. And so I looked at the votes for the project presentation. So probably the best day, which is available for everybody except 2 people, unfortunately, is June 5, Wednesday afternoon. I think the slot was the middle slots of 12:30 to 12:30 plus 4 hours. And I think that's pretty much it for the technicalities. So yes, so I was in Canada for 2 weeks, studying artificial life. So here you can see a picture of the biggest catch of the 2 weeks. Okay, so the only problem is that I kind of 2 weeks is very long, so I kind of forgot about which day we were, and I forgot that I was coming back. Actually, came back in Switzerland yesterday afternoon. So today's course was prepared quite fast. So it will be more high level. It will be a presentation of a lot of different agent-based models. I will not have the time to go into the details. Also, I didn't have time to study the details. And so, yeah, keep that in mind for today's course. And I forgot to start the recording. Okay, perfect. Hopefully we're streaming because the MacBook decided to do an update just before the course. I think should be fine. My father will call otherwise. Okay. So agent-based models. So what are agent-based models? So up to now, most of the models that we have been looking at were kind of physics or chemistry based. So the philosophy was that we take very simple building blocks, which have very simple interaction rules, and we rely on scaling the system to a bunch of particles to allow for some complex behavior to emerge. Okay, so we really relied on the scale of the system for this complexity to emerge. Okay, from the simple rules that we chose. And so today we take a look at a different approach, which is kind of trading the scale of the system for a smaller scale system, and increasing the complexity by increasing the complexity of the elementary rules of the different components. Okay, so we trade off scale, so we win in the scale department because we need to scale our system less, but we lose in terms of complexity of the rules because we need more complicated rules to still have interesting behaviors. Okay, so instead of the elemental building blocks to be like particles or pixels, like in the game of life, for example, we have more complicated components that we call agents. Okay, we call them agents because they have some sort of internal state. They kind of can think about what they will do. Okay, they are much more complicated components. Okay, so we'll see that in practice, actually, the models that we'll see today, in some of them, you might say, okay, this is not really an agent-based model because the rules of the particles are very simple. So we'll see that the line is not so clear on what would mean to have an agent. But in general, it is more complex based behavior. Right, so as I said, so this can be seen from the point of view of the inspiration of these artificial life systems. This can be seen as changing a physics or chemistry-based simulation, where you say, okay, we have simple particles, simple rules, and take a bunch of particles, to a somewhat biology level simulation, okay, or even higher level, like a city scale simulation, something like that. So you start with some complicated components, let's say a cell or even an animal, for example, and it has complex decision-making procedures. And you have much less elements, of course, because you simulate directly at the level of animals. So you need, okay, if you want 10 animals, you need 10 base elements. Whereas if in the physics simulation you want 10 animals, you need probably 10 to the 25 particles, right? So in this case, you might say, okay, well, that's kind of cheating because we're saying we want complexity to emerge. But if you start with a very complex system, what is emerging? Okay, you're just putting it in and it's not emerging. So it's kind of true in some sense, but what we'll try to aim for here will be both the complexity, the emergence of complexity in the interaction of these sophisticated agents. Okay, there might be some interactions between many agents which would not expect, so it would emerge, and as well as the design of the agents. Okay, so since the agents are very complex, they have a lot of moving parts. And so it's usually very hard to design an agent for a specific goal, right? And so in that case, the emergence of the complexity will be through the evolution of these kind of levers that govern the behavior of the agent. And so the complexity will be the agent itself becomes more and more complex, can perform more complex tasks as it changes in time. Okay, so that's the basic idea of agent-based models. So let's look at some examples now. That's all we're going to do today. So let's start with basic agent models. So when I say basic, I mean that the agents themselves are not very sophisticated. Okay, you can even consider them as particle systems sometimes. So yeah, so these constitute kind of the intermediate state between complex agent-based models and the simple particle or cellular automata system that we've seen until now. Okay. So the reason we still call them agent-based is because their inspiration, as we will see, comes from complex behavior, for example, of birds. Okay, we say that one particle represents one bird, and of course the bird in reality is a complex decision-making behavior, and so we still call them agent-based, even though you'll see the rules are not that complex, actually. So the first one I want to mention is BOIDS. Okay, so BOIDS is an artificial life systems that has been developed to kind of understand, or more like simulate, this kind of flocking behavior that birds have, or also fish. Okay, so here is a huge flock of birds, and as you can see, they form very coherent kind of groups, which have a coherent speed. And this is pretty impressive because the number of birds here, I don't know what it is, but it's certainly in the thousands. And it seems to be a very coordinated behavior. Okay, but of course, we do not expect birds to have some kind of leader that says, okay, let's go in formation and fly in the same direction. So we expect this behavior to actually be emergent from some sort of simple rule that each bird applies, right? Because the birds are all indistinguishable from all intents and purposes. Okay, you don't have special birds that lead and other that follow. And so this is what BOIDS aim to do. Okay, so what does BOID mean? BOID stands for birdoid object. Okay, so it's a bird-like object or agent. And it was developed by Craig Reynard. So this BOIDS systems is an example of, again, self-organization. Okay, so in that case, yeah, agent-based model because it's based on birds, but not really. Okay, the rules are very simple, and it's a great example of self-organization. Okay, the same way that the neural cellular automaton was an example of self-organization. Starting from simple and local rules, you can get global organization on a global level. Okay, so how does it work? Let me just check. Yeah. Okay, great. Right, how does it work? So in BOIDS, you have each bird, which is represented by a triangle here, that has a velocity. And this velocity is simply adjust at each time steps according to 3 driving forces. Okay, so the birds follow 3 simple rules to choose how to adjust their velocity. So the first rule is separation. Okay. So this is simply the tendency of BOIDS to avoid collisions with other BOIDS, right? So this is very simple. How does it work? It's a repulsive force that acts between BOIDS when they get too close. Okay, so this is an example here. So you have the green BOID here. The circle is its observation radius, what it can see. And so it can see 3 other Boyds in its radius. And what happens is that you apply simply a repulsing force, which is is the same force as the electromagnetic force between 2 electrons, for example. So it decays as the Boyds get further away, and it becomes stronger and stronger as they get closer. And so this force repulses the Boyds such that they organize away from each other. Okay, so that's the first kind of piece to avoid having all the birds collapse into one point when you make them flock, right? The second force is velocity alignment. And so this, although it doesn't seem like, is also a force which prevents collisions, right? If the velocity of all the Boyds are aligned, they will not collide, of course, because their velocities are parallel. So how do we align the velocities? Well, again, it's very simple. It looks at the Boyds in a certain radius, computes the average velocity of the surrounding Boyds, and a force is applied to match this average velocity, okay? So this is depicted here. So the current velocity of the Boyds is this green line. This blue line is the average velocity of the surrounding Boyds, and so a force is applied to steer towards the average velocity. Okay, this is the second rule. And finally, the last rule that we need is cohesion, okay? So a rule that allows for the Boyds to form groups. Because so far, with this, if you launch a simulation only with these 2 rules, you will just get Boyds that kind of spread out and go in the same direction, but they have no reason to form groups that fly together. So the last rule we need is cohesion. And so this is the final driving force that makes Boyds sticks together. Of course, this rule is in competition with the separation rule, and we have to see how to arrange them both. But what happens is that, again, you look at the radius around you, you compute the average position of the Boyds around you. So this is the center of mass of the surrounding Boyds. And you will steer your velocity to be in the direction of this center of mass position. Okay, very simple. So these are the 3 rules, and they each produce different forces steering the Boyds. But we must still understand how to combine them, right? Because a lot of the time, some forces will produce forces in different directions. So how do you choose which one to apply? So in the simplest Boyd model, the original one, the Boyds, they have a capped velocity from above and below. So they cannot go slower than a certain speed, and they cannot go faster than a certain speed. Okay, this is to prevent, of course, not going slower is to prevent Boyds from stopping. And not going faster than a certain speed is necessary because all these interactions, they do not preserve energy or whatever. So if you do not put a max velocity, you will have situations which Boyds get just a positive feedback loop and they accelerate to infinity. Right, so in the original paper, surprisingly, there is no equations actually. It just describes at a high level all these rules. But it gives some direction on how to combine this force. Okay, so what it says to do is that you compute an acceleration for each of the 3 forces independently. Okay, so you apply these 3 steps and you get 3 accelerations or forces. What do I say? Direction of acceleration is obvious, so this does not matter. Okay, so the magnitude of the acceleration. So the magnitude of this computed acceleration, because from what I told you here, all you get is a direction for the acceleration, right? I don't tell you how much you should accelerate in this direction. So for cohesion and velocity alignment, the acceleration vector has a fixed magnitude, okay? It does not depend on anything else. Whereas for separation, the magnitude of the acceleration will decay with distance, okay? So the closer you are to the Boyds, the higher the magnitude of the acceleration will be, okay? And he says that using a R² decay, so just like gravitational force or electromagnetic force, works well, apparently. But this is all very, finicky. You just have to try and see what looks good. And so now we have to combine the 3 accelerations. and you have different ways to do that. Either you average the three accelerations. Okay, this seems sensible at first, but if you think about it, in some cases it can be very stupid. Okay, so for example, if you have one acceleration force, for example, you are at a corner somehow, and one acceleration force is telling you to go north to avoid the corner, another one is telling you to go east. If you do the average, you go northeast, you will go exactly towards the corner. So this is not always good, but in practice, it actually works very well. So another proposition that he does in the paper is to use only the largest magnitude or the largest delta between the current velocity and the acceleration. Okay, so in some sense, in this case, you always steer towards the most urgent change, right? And this also works, but you tend to get some kind of jittery movement, right? When, for example, the cohesion and the separation force are more or less equilibrated, at one time steps, you will adjust your velocity just according to the cohesion. The next time step, just according to separation, and you tend to have some kind of jittery movement. And the most, let's say, sensible thing to do is to have some sort of acceleration quota. So you have a max acceleration magnitude that you're allowed to apply each time step. And you put priorities on the three forces, so which one will be added to the total. And so you keep adding to the acceleration quota until you spill out of the maximum quota, and at which point you just stop adding and you clip. Okay, so for example, if the max acceleration magnitude is 3 in some units, the separation force adds, let's say, a magnitude of 1.5. You add it to your total quota, you're still under, you're good. Alignment adds 1 to the total magnitude, 2.5, still good. And then cohesion adds 2 to the total magnitude, so you clip it to 0.5 and add it, okay? Something like that. And so in this way, you still have a hierarchy of forces. So you can kind of prioritize the extreme emergency situation where you have to kind of allow all the quota to one direction. But still, you combine the different positions together, so you get less jittery movement. Okay, so yeah, that's pretty much it for Boids. So I thought I had a video here, not yet. Ah, yeah, right. So there is this website here that you can try, and right. So let me slow down the speed. Exactly. Okay. So it looks like this. So as you can see, oh yeah, what I didn't say is that you can also add some randomness on the direction of the bird just to make things more natural. I think there is some randomness in here. I'm not sure. Yeah, movement randomness 1. So if you reduce the randomness here, right, it looks pretty much the same actually. Yeah, so you get these kind of flux that form and how do you say? And this band, and you have a bunch of parameters here you can play. So Boyd's vision is how many birds do they see around them. So here you can say you have some problems here because you have some points which have a super high concentration of bird. So this is typically not wanted, so you should increase the separation force in this case. But it seems that here it's increased too much, so the groups are too high. Okay, lower the vision to get some smaller groups. Then you have, again, steering force. How much does the steering impact the magnitude of the acceleration? Cohesion force, if you increase it too much, of course you collapse into point-like flux, which is of course not good. That's what you need the separation force. Same thing, if I put the separation force to 0, they also collapse to points. So you can see why you need that. And as you change the parameters, what's interesting is that you seem to have some sorts of phase transitions. Not too sure. So here the magnitude is a bit small. Let me see if I can increase the number of Boids. I can, but it's too crowded. Yeah. Right. So this is what Boids is. And okay, it's an artificial life simulation because it simulates flocks of birds, but it has been mostly used for actually for aesthetic purposes. Okay. For example, in video games or movies, when you have to have a convincingly looking flock of birds, you will typically use a Boid's algorithm because it's very hard, of course, to animate each of these things independently, right? So yeah, so this is Boids. So let me show you a simulation here at much larger scales so that you can see what the phase transition that I'm talking about. So let me, it doesn't let me. Okay, whatever. Okay, so this is again the exact same algorithm, but with pretty colors and at much larger scale. And the guy just plays with the parameters. So you can see here, cohesion factor, separation factor, alignment factor, and then neighborhood radius, which is of course very important. I haven't talked about it, but the amount of birds that each Boids can see obviously changes the behavior. Yeah, so you can see as he changed parameters. Yeah, I'm not sure if I can call them phase transition. I'm pretty sure they are if you go to even higher scales. But there are phases where you have kind of a unified group in all the screen. There are phases which are, I suspect, is some kind of phase transition points where you have different size of flocks that form, independent flocks which are several sizes. And then you have the phase, of course, where the flocks completely collapse to points or lines. And I don't know if this has been studied actually from a physics standpoint, whether it's a generate phase transition, you compute critical exponents, etc. But there was a paper. Let me see. Oh, yeah, okay. Let me come to this later. But I will mention a paper that kind of does a more physics-based, how do you say, study of birds' flocks. Okay, so yeah, so this is the Boid simulation in its purest form. So as you can see, it's quite simple, right? Each bird does not a lot of computing to determine its direction. So you could kind of see it as a particle simulation with some peculiar forces between the particles. So it's really at the edge of what we call agent-based model. But you can push further in this agent direction, right? So you can add additional rules to increase the complexity of the decision making, okay? So the Boids, you can add, for example, a small neural network that will take into account the position of the surrounding Boids, feed it into a neural network, do some random computations, and then map it to an acceleration for the Boid. And then if you run simulation at large scales with many Boids, many things, you can actually select for some behaviors, okay? So you can add, for example, predators that will try to eat Boids, and then you could develop some sort of kind of defense strategies as fish do when they defend against predator using some flocking behavior. And of course, you can add, more simply, you can add obstacles such that the Boids avoid the obstacles. This is very simple. You just add a repulsive force on the solid blocks, okay? And when you do this, you get actually really, really lifelike behavior. So let me show you here a simulation from YouTube video on Boids. So the obstacles are really nice because they break kind of the cohesion of the group, and that's where you really see emerge this kind of behavior similar to the birds we were seeing in the beginning. As you can see, they still manage to keep in groups, but they split to avoid obstacles. And here is in action into a small kind of video game world where the flocks or the groups, schools of fish are made using a Boid simulation. Okay, so as you can see, it feels very natural, very lifelike. And that's the main application of the Boids, I must say. I don't know of very advanced application in the artificial life direction where they're really used to simulate some sort of complexity emergence. But yeah, and here is a simulation in 2D again, where you add some predator fish. And I think in this case, the predator don't really need to eat or whatever. They're just, their rules are to follow kind of the closest fish. And the fish are also repelled by the predator more strongly than the separation force. And what's interesting is that you can see some behavior which is similar to what, or at least qualitatively similar when you watch these documentaries and the shark like dive in the school of fish to kind of eat one fish. So here, let's go forward to the examples. Yeah. And yeah, what's interesting is that, yeah, so this really at the moment where Boids was kind of developed, it really showed that you don't need this. Some people thought, and there were some models of flocking, etc., which were based on some kind of leader dynamics. Okay, some people were saying, okay, the birds look to one specific bird and they kind of follow its direction to make the flock. And the Boyd simulation shows that you really don't need something like that. Okay, all you need is to look at your neighbors, do kind of something with your neighbor, coordinate with neighbors, and that's enough to get flocks of considerable size. And so, yeah, so this is Boyd's. And the last note I wanted to mention about Boyd's is this paper here, Statistical Mechanics for Natural Flux of Birds. So in this paper, they consider, again, they want to try and explain flocking of birds, as we have seen in the first video. And to do so, they actually model the birds by spins. Okay, not everybody's a physicist here, but you have a very simple model, which is used a lot in physics, which is the Ising model. It just describes how magnets work. Essentially, it's a model of magnets. So you have spins, which are, you can see them as just some small arrows that can point in one direction. And spins tend to align with each other, with their neighbors at least. And so they want to align with each other, and then you add some noise, which is some temperature that makes them kind of vibrate and tends to misalign them. And when you scale this model, okay, you observe some kind of grouping of the spins. And so in this paper, what they did is that they modeled the birds with spins, and they mapped the free parameters of this model, which is simply to how many spins each spin is connected and the strength of the connection. And what they saw is that very convincingly in the data, when they try to fit this model, they find that each spin or bird is connected to approximately 21 other spins. Okay, and this they tried to fit the model to different flock densities, different bird, not different birds, I think, the same bird but different flux density. And they saw that it was always 21 neighboring birds. Okay, so what that seems to suggest is that the Boyd's model is actually wrong in what happens in reality, because the bird is not looking at some fixed radius distance around it, but is looking at a fixed number of birds. Okay, so if you take a flock which is much less dense, the bird will in fact look much further to match its velocity to the 21 neighboring birds. Same thing if you get a denser flock. Okay, so this could suggest, I don't think it has been done, I'm not sure, a different improvement to Boyd's, where instead of having this radius of interaction, you would have this constant monitoring of the 21 closest birds, for example. Okay, and this presumably would be more, more realistic, according to this paper, at least. But of course, much harder to implement because you have to compute the 21 closest birds, and it's pretty hard. But it's interesting to see that you can actually come up with such a prediction with such a simple model as the Ising model. Okay, so I wanted to mention that because it was nice. Yes, question?
Is there anything about how birds see actually, because they don't see their back?
Right. So in this, exactly. So in this Boyd model, good question. In this Boyd model, the birds look at a radius around it. There are other Boyd's model where you reduce these fields of vision to be just in front, and it gives qualitatively the same behavior. So it does not impact so much. And I think that birds have a pretty wide view because their eyes are on both sides. So they can almost see a circle around them. And then there are also other considerations which are not taken into account in Boyd's, is that in the air, birds can see, of course, much further than a capped radius. Okay, and so this can explain some behavior that is observed but not replicated by these models, in which sometimes you have two flocks of birds away from each other and they kind of come together to merge. Of course, this cannot be explained by either of these models. And here you need to add some sort of long-range interaction where you can see birds far away, but okay. So there are many improvements, but even qualitatively, it gives very good behavior from these rules. So this is Boyd. Any other questions? All right. So let's move on to slime modes or ant colony simulations, which are also quite similar to Boyd's, but a little different. So slime molds, I will not go into depth about the biology, but they are a unicellular system. So it's a single huge cell, if I'm not mistaken. And okay, sorry for the interruption. I just have to edit a little bit the video because the video I used to show the slime mold was had some problem with copyright, so I made another one here. So the only thing I wanted to show is how this slime mold behaves in real life. So you can see that it expands in kind of a broad way, kind of exploring all directions, which is a bit reminiscent of these pathfinding algorithms like Dijkstra's algorithm and stuff like that. And usually when it finds a food sources, it creates a highway, which is presumably close to the shortest path between whatever its center is and the food source. So this we'll see here, the kind of highways that get created after the food source is found. So if we wait a bit, yeah, you can see here at the end, kind of the broad parts evaporate and we are left with these complex paths that transmit food from one part to another. And yeah, so back to the present. Okay, so, yeah, here it is. So the nice thing about slime molds is that people notice that if you take kind of a barren landscape and place food at some specific location, the slime mold will kind of grow and form a network of slime channels, like so. So these are oatmeal bits. So the slime mold kind of expands to look for food. And when you find a food source, if you wait long enough, it forms, yeah, you can see them forming here, some channels to funnel the food along the body, okay? And of course, from an optimization standpoint, the best thing to do would be to have the shorter channels to kind of distribute food more effectively and use less matter to do so. So the slime molds should, in principle, be incentivized to find the shortest path between all these food sources. But this is, of course, the traveling salesman problem, which is a NP-complete, NP-hard, okay, NP-hard problem. So you have no kind of good solution to it, but you can have some heuristics. And so this is a fun experiment that some people did at some point. They put the food bits at the position of the metro stations in Tokyo, and they let a slime mold kind of expand on this food network. And then they mapped the mold network that resulted from this configuration. And when you compare it to the actual Tokyo metro network, is quite close, right? So, so it was very able to find a very good kind of shortest path between all these points for food. Okay? And the question is, how does it do that? Obviously, it's not running on a pathfinding algorithm. So how does it work? So yeah, similarly, if you have already observed ants, they often form some sort of highways between different points of interest, either nest or food sources. And they're very good at exploring their surroundings for food, right? Without any centralized coordination. So this is the same behavior we observe in the slime mold. And so the question is, how do they do it? And so in these models that I will present, we try to kind of capture this self-organizing behavior and try to understand how can it emerge from these simple rules. Right, so slime molds. So there is this paper. So for any chapter, I link to a paper or to a resource if you're interested in more details. So in the slime mold models, we have a bunch of particles which always have a constant speed, right? They can only affect the angle in which the particle is moving. And when they move, they deposit some sort of, you can see it as a chemical behind them. And this chemical, over time, they both diffuse and decay, right? So the slime mold particle decides to steer according to this chemical which is deposited. Okay, so it looks in front of it at the chemical that is present, and it will tend to, with some randomness, to steer in the direction of the higher concentration of the chemical. Right, so you can expect this to create highways, because if a slime mold passes and deposits the chemicals, then this will attract more slime mold particles, which in turn will deposit more chemicals, and so you have this kind of positive feedback loop that creates highways where all the slime mold particles will follow. And so you have the creation of these microscopic networks of slime molds. So we have this picture from this very nice website that I suggest you to take a look at about how it works in practice. So this is a slime mold particle, and it senses in 3 different locations in front of it, okay, to simplify things. Then it chooses to rotate its angle. And so here you can see the different cases that are in the slime mold model. So if the most concentration is in the middle, you have no change in direction. If you have equal concentration on both sides, you just choose a random turn. If you have more concentration on the right, turn right, and so on. Then once you have decided on your new direction, you move according to your speed, and you deposit some chemical. Then the chemical diffuses. So how do you diffuse the chemical? So you can apply either the diffusion equation, but it's kind of overkill. What we do in practice is just you apply a convolution with a kernel which is uniform. Okay, so this will tend to spread out the particles, and this is good enough for the model. And after diffusion, you decay the concentration of the chemicals. So all chemicals are kind of consumed over time. You can say that they evaporate. And you apply this loop over and over again. And if you put enough agents or particles, you get some really beautiful results. So here is a video as an example. So let me show you first. Yeah, so these are the different steps. So here you have just particle diffusing the chemicals behind them. And here we add the actual following of chemical trails. Let me forward here. Yeah. And this is what happens. Yeah. So as you can see, the particles converge into path. And of course, you have still some randomness, right? Sometimes the particle just chooses a direction which is not aligned, just to break the symmetry of the initial configuration. So this is with a low number of agents. So if we increase the amount of agents, that's where we get something which is surprisingly beautiful. I wanted to implement this one. I didn't have time to. I will try to do it for next week. But you get these sort of things, yeah. So you very quickly get these highways, and over time they collapse, right? They tend to there is some sort of elastic force that emerges. But what's interesting in this example, at least with these parameters, is that there is some instability, as you will see. And at some point, it just explodes, yeah. And of course, when the particle reaches the border, in this case, you have random reflecting conditions. So this also causes an explosion, as you can see in the bottom here. Whoops. Yeah. So you get these networks. And you have a few parameters to play with. So you have the strength of the steering mechanism when you encounter some concentration of chemicals. You can play with how fast do the chemicals decay. You can play with how random the movement of the particles are. You can play with how fast the chemical diffuse. And as you change this, it changes the behavior a lot. So here there are a few examples that we'll leave to play because it looks very amazing. So here is what happens as you change the different parameters, right? This is not the behavior. When the color changes, the parameters are changing. Sometimes what you observe is kind of reminiscent of reaction diffusion. So there's probably a connection somewhere. Yeah. But it really makes some beautiful behaviors. Right. And okay, this is another example where instead of having just one species, you have different slime particles, and the slime particles can either follow the trail of other particles or their own trail. You can kind of mix and match everything, and then you can get those interweaving patterns between species. And this looks even more like reaction diffusion. Right. So these are slime molds. Any questions about the slime molds? All right. And then very similar to slime molds, let me mention this and then we go into the break, is ant colony models. Okay, so this is almost exactly the same algorithm. So you have agents that deposit some pheromones, some chemicals, and when they decide where to steer, they steer towards the higher concentrations. The main difference in ant colony algorithms is that they can deposit different types of pheromones. Okay, the simpler example is when they can deposit two. Okay, when an ant is looking for food, it will deposit the kind of a blue pheromone, let's say, and this blue pheromone should be interpreted as this pheromone is a return path to the nest, right? Because the ants start from the nest, and so it lays a return path to the nest as it's looking for food. And whenever an ant finds food, it changes the type of pheromone that it deposits. Okay, when it's carrying a food source, it will want to come back to base, so it will follow the blue pheromone, but it will lay down a red pheromone, which will indicate path to the food. So that when it's looking for food, it will follow the red pheromone, or the green one in this case, sorry. And so if you use these rules and you put a lot of ants together, you will find that they actually solve, or it's a pretty good algorithm to solve the traveling salesman problem. Okay, of course, it's not an exact algorithm, it's a heuristic. You will not always find the best solution, but we'll often find a very good solution. So let me show you here it works. Yeah, so here you can see the two home markers as the ones that are deposited when they're looking for food, and the green ones are the ones that are deposited when they're bringing food back home, right? And the size of the markers, again, is their intensity, and over time they also evaporate. Here there is no diffusion, I think. You can also add diffusion if you want. And so at larger scale, this is what happens. So the ants just scatter randomly. When they find a food source, they start carrying the food, but they go in random directions, right? Because, of course, they don't know where home is. Or they don't know anymore because the to home path has evaporated. But at some point, they do find a path to home, and this very quickly forms a highway, okay? So the way that this is a good heuristic for the traveling salesman problem is pretty simple to understand. So if you have two paths connecting two nodes, and one path is longer than the other, it will take more time for an ant to do a come and go, aller-retour, right? So since it takes more time for the ant to come and go, there will be less pheromone deposited on average than the other path, which is more quickly threaded. And so this path will tend to kind of evaporate faster than the shorter path. And so the shorter paths will be more likely to survive. Okay. So here in this case, I don't know if we really see that, but yeah. So you have this path, which are clearly suboptimal because they are, okay, this is not long enough. So when the path is first formed, they have curves. What's happening? Oh, yeah, my computer is turning off. 1 second. So you should see the path that straightens over time as it matches the shortest path. And yeah, so these are, again, some simulations which looks nice, etc. But the ant colony optimization algorithm can actually be distilled to an actual algorithm that you apply to solve the traveling salesman problem. Okay, it's much more abstracted. You don't need to simulate the ants going from each point to another, but it can actually be used as an heuristic algorithm to solve the traveling salesman problem. Yeah. And right, I think we'll stop here. So let's come back at 1520 to continue on some particle-based, and then we'll go on to the proper agent-based models. Okay. As usual, I'm going slower than expected. So yeah, so these were two simple agent-based model, almost can be considered particle-based models. So while we're at it, let's look at a few more particle-based models that I think I've mentioned, but not gone into details. So the first one is particle life, and there is a whole host of other particle-based methods, but I think this one is the most beautiful and maybe the most famous. So the physics is again pretty simple here. So the world is composed of particles of different kinds, which visually they are distinguished by their color. And each particle interacts with the surrounding particles using this specific force function. And this force function depends only on the distance between the two particles. Right? A very simple force function. So completely radially symmetric. And the force is always applied collinearly with the particles. Right? So it can either attract the particle or repel the particle. It cannot kind of push it around in other ways. And the force function that you apply depends on the pair of particles that are interacting. Okay, so for example, say you have red and green particles. You could say that the green particle will be attracted by the red particle, but nothing stops you from saying that the red particle will be repelled by the green particle. Okay, you don't have to respect Newton's third law of the exact and opposing forces. And in fact, you should not respect it because otherwise you won't get any interesting behavior. So the force depends on the pair of particles that interact, and it can either be attractive or repulsive. And you also add, again, to prevent collapse, a repulsive force below a threshold, okay, which is always present. And the type of forces you can take can be many different things, but you don't need to be very complicated. The one that is used in the videos that I will show and usually used in this model is piecewise linear. So if you have beta, this is the threshold of repulsion, which is always here. And then you have this single parameter A, which will vary according to the pair of particles that interact. Okay, so if A is positive, here the convention is that it's attractive. If A is negative, it is repulsive. And as you can see, the force has some maximum radius of interaction. So above a distance of 1, the particles do not interact. And yeah, one important thing to notice is that this interaction of particles does not conserve energy. So in part because you don't respect Newton's third law. So you can have examples where the red is attracted by the green is repelled by the red. So if you just put this in, they will just self-accelerate each other to infinity, and so you have problems. So what people do is simply to add a viscous friction to keep velocities under control. So the equation of motion for each of the particles is very simple. It's just the acceleration is minus some friction coefficient times the speed, plus the force, which is the sum of all the pairwise interactions. All right? So if you do this and you put many kind of particles with different interactions, you get this sort of behavior. So you very easily get these sorts of networks and also very easily get solitons. And this is because of this kind of repulsion attraction mechanics, where if a particle is repulsed by another, but the opposite effect is to be attracted. So here you have the purple is repulsed by the blue, but the blue is attracted to the purple. You naturally get some trains of particles following each other. So they can combine together and form this sort of solitons very easily. So this is the kind of behavior you see. You can see things like eating other molecules. They just get attracted and they fusion. Yeah, there is not much more to say to that. This is just the explanation of the rules. I wanted more videos, but yeah. So, okay, you get these sort of things. I haven't seen it do things which are very impressive. Like, of course, it cannot really reproduce. These are numerical problems. Cannot really reproduce because the number of particles is finite. Okay, it might kind of separate, have some kind of mitosis, but it's kind of limited. And okay, you get all sorts of these nice solitons, but beyond that, I don't know much more about this model. It looks nice, and that's a very common particle model, and you can try it for yourself at this website if you want. Okay. And this is one last model that I wanted to mention. So this is not a famous model, whatever, it's just something I coded very quickly on a train ride. And it's just, I just want to show it to you because I want to mention some of the challenges when you have to do a particle system or an agent-based system. So the model is very simple. The goal was to get something where you have particles that form something like atoms. So I wanted a nucleus of particles with some electrons orbiting around. So I have three types of particles: protons, the red ones here, which are positively charged and heavy; neutrons, which are neutral and heavy; and electrons, which are negatively charged and light. Okay. And the interaction that exists are the following. So protons and neutrons interact with the strong force. It's in pink. And the strong force is very simple. It's modeled as a spring with a high constant of interaction. So it's a strong spring. But to make it so the interaction is very local, so it does not interact at large distances, I decay it with an exponential decay. Okay, so the force formula is this one here. So R is the distance between the proton and the neutron. Ls is the rest length of the spring. S is the strength of this force. And here I put an exponential suppression on the strength of the force. So the force will have a radius, an approximate radius of interaction of size RS here. Okay, so here we have three parameters. The size of the spring, so how close will the protons and neutrons get, the strength of the spring, and the extent in which the force acts. Okay. Then you have proton and neutron. They repel weakly with the same formula, but a smaller s at small distances. Again, this is the usual thing to avoid to have things collapse into a single point. And then proton and electrons, they interact by the electromagnetic force, here in yellow. So this is a usual electromagnetic with a 1/r² decay. And finally, I needed to add something because with these forces, which are with this electrical force, it will be very complicated for electrons to orbit the protons, right? Because this is very unstable, especially if you have other electrons and you have many electrons in the orbit. So I added an extra force which will lock the electrons in this kind of orbit distance. And so this is again, this is now a weak spring, okay? L is the spring constant, with the same force as the strong one, just at a larger radius and between proton and electrons. So what will happen is that the main interaction between protons and electrons will be the electromagnetic ones, but if the electrons settle at some specific radius, then they will be locked in the orbit by this extra force. And yeah, the reason I choose this force is just to try and create some atom-like structures. And all these ad hoc springs that I must add is simply because in practice, to form atoms, you need quantum mechanics, and it's quantum mechanics that allows you to have these locked-in orbits for the electrons. Okay. With classical mechanics, it's much harder to do. And so this is the sort of behavior that you obtain. So I forgot to say, I also added an overall viscous force, which is very weak, but it's there. And so as you see, when you start, there is too much energy in the system. So things start orbiting each other, but they're not very organized. But as time goes by, things get slowed down by the friction force. And it starts to form the sort of atoms that I wanted it to form. So here you can see one which is pretty nice. So the neutrons are in green, the protons in red. And so you see that it forms a nucleon of both protons and neutrons. And this is because the strong force is only between protons and neutrons. It's very weak between proton-proton and neutron-neutron. So you form these atoms. Sometimes you have some extra orbiting particle, which is nice. And so the problem is, of course, since I have this viscous force, and there is no way to add energy into the system, as you wait around, everything settles down into a perfect atom like so. So here you have some sort of hydrogen atoms, just a proton and an electron. These are some higher form of atoms. And you can see that it even organizes more neatly with the neutrons in the middle and the protons on the two sides because of the electromagnetic repulsion of the protons. So it works quite nicely. Okay, it will not anything will emerge, but the goal was to exactly have that. And it works. And the main problem with particle systems is that the computation, unlike a cellular automaton, in a cellular automaton, if you have n cells, the complexity of the algorithm is O of n, right? You update each cell once. With particles, you usually have forces between pairs of particles. So in principle, if you have n particles, your algorithm will be O of n squared. And that is very bad if you want to scale the system. So the way that people do to kind of mitigate this problem is that as we have these forces which decay with distance, which is usually the case, okay, you don't want forces which are kind of instantaneous between faraway points. You can do a simplification in which you just compute the forces of the neighboring particles. Okay? You disregard all the other particles because their contribution is negligible. So in practice, what we do is that we partition the world into squares, and you choose the size of the squares to be approximately the size of the interaction range. And so this gives you something like this. So the square color is the number of particles in each square. And when you want to evolve the particle, what you will do is instead of looking at all other particles, you look only at the surrounding squares. Right? So when you update a particle, you make it interact only with the particles in the surrounding squares, and that eases your complexity because you will not interact with all particles each time, only with particles around you, and the behavior will be essentially the same. Of course, this is problematic as you go forward. For example, in this simulation, as you have these atoms that are very bunched up together, most particles are anyway in the same square. So in this case, you get again the worst case complexity of n squared because all particles are at the same location. And so it's good if you expect your particle system to be somewhat uniformly distributed, not all concentrated in a point. If you have bunched up particles, you can do other optimizations, which is when particles are very bunched up together, instead of doing the interaction with each particle independently, you can consider them as one big particle and do the interaction with the center of mass of this big thing. So there are a lot of optimization compared to cellular automata, which are pretty hard to implement and even harder to implement on the GPU. Right? So that's why particle systems are not that comfortable with them because they're much harder to implement from that point of view. They're not as easily, their behavior is not as easily translatable into parallel computation as cellular automata, for example. But they are very important, okay? And for agent system is the same thing. Usually we want agents to interact with their environment and with other agents. If every agent must interact with all other agents, it gets hard. So you should implement some sort of optimization like this. And so particle simulation are a whole field of research. And so there are thousands of optimizations which are possible, but it's just something to keep in mind when working with these kind of models. Okay. So we're done with this kind of particle systems. And now let's go to actually agent models where the agents are actually more complex. So right, so the main thing to keep in mind with these agent models is that they often have a complex decision-making process, which is usually pretty obscure. Right? It's not some very simple instructions. You have a bunch of parameters that interact together to make a decision. And what you usually want to do is to seek evolutionary behavior on this decision-making process. So you want the creatures to evolve and to kind of make better decisions, et cetera, et cetera. And so to do this, you need a mutation-friendly way to encode this decision-making program. Okay? It's not good if your decision-making program is a small Python program, because it's very hard to do a mutation on a Python program that does not break the program. So usually, what people do when they do this agent-based model, they use a language that, quote unquote, always compiles. So a language that no matter what you change in the language, it always produces some valid output. It might be garbage output, but it's always valid, at least. So the things you can do is that you parameterize the behavior with some meaningful real numbers. For example, I don't know, strength of rotation, or how many particles, how many agents are in the field of view, something like that. Or by using neural networks. Okay, neural networks are very good because we know that they can kind of represent any function that you want, but they always compile, right? No matter what weights you choose for your neurons, you will always get some kind of output. And so they're very good for mutations, right? Because you can mutate the values of your neurons a little bit. You're sure that you get a neural network that at least works. And you can also use other things which are flexible codes. So there are some coding languages which are completely flexible. So you can add and remove basic operations, and the code always runs no matter what changes you make. And so you can also use that. So let's see at some concrete examples. So the first, maybe oldest one of these agent-based models is Tierra and Avida. I think I mentioned it already in one course, but I don't remember which one. So this is an agent-based model in which each agent is a very small program using one of these very simple programming languages. So it can do some basic operations like AND, NOT, copy memory, paste memory, move the reading head, etc., etc. And in this alive system, the agents act directly on the memory of the computer. Okay, so they live in the memory and they can act on the memory. And so they can essentially take their own code, read it from the memory, and then paste it somewhere else in memory, and that's how they reproduce. And so there is a natural competition that arises because the memory has a finite space. So this is a representation of what's happening. So this genome is just the code for the creature. So it's a bunch of instructions. And it also determines the size of the creature, the size that is occupied into memory. And it has different heads to read, write, etc. And okay, it acts on the memory and it can copy itself, parasitism, etc. And so you can just start with a population. What happens usually is that the world is seeded with some ancestor organisms. So these ones are handcrafted to be able to duplicate. And then you add mutations to the duplications and you wait and you get some sort of evolution. So it looks something like this. Let me see if I can run this. Right, so the squares here, each square represents a program. And the color of the program is let's see, I think, yeah, I don't know if the color of the program represents the fitness or just the kind of program. But we can see that here if let me see, how can I save this again? I forgot how to save the thing. I just drag it here. Okay, so we can go into the organism, take this one. This is the code of the organism visualized. And so if you run it, this is what the organism does. So that's what it writes into memory. So you see the three heads here, the reading head, the copy head, etc. And so it makes an offstring at some location in RAM, which is free. And then there is some mechanism for the things to die, etc. So you see that the offspring is mostly the same as its father, but there are usually some mutations. For example, this K here has been added. Oh, sorry, it's a V that mutated into K. And so as you let the thing evolve, in principle, you get some nice behaviors like the creator says that you have parasitism. So there are some codes that cannot reproduce on their own. So they just go and read the code of another creature to kind of reproduce themselves. So it's some sort of parasitic behavior. Then you have symbiosis, where two organisms have to cooperate to reproduce, and so on and so forth. It's very abstract, because when you see this, you don't see much. You see some colors, sometimes taking over, sometimes dying. But yeah, so this is a typical example of an agent-based model, because each pixel has some very complicated function that it acts. Okay, it's very different from the game of life. It has this whole code, and each pixel is executing this full code. So that's a typical example of what we mean by agent-based models. And so here, what we're looking for is this sort of thing, right? Some emergence in the behavior of the organisms, both their intrinsic behavior alone, okay, how do they manage to find a way to reproduce effectively, and both an emergence in the interaction between the different species, okay, parasitism, symbiosis, cooperation, etc. So it's different from the emergence we were looking before, which was more like self-organization, emergence of solitons and creatures and stuff like that. So the other one, which is very famous, and it always surprised me how old it is, despite how cool it looks. I showed this in the very first course, is CAM-SIMS evolved creatures. Okay, so this is an example of a model where you have complex agents, but you don't let them interact together. It's just a single agent, and we just look at the behavior of a single agent. And so the complexity is in how it evolves over time. So how does it work? So you have this agent, which is parameterized by a graph, a directed graph, along with some bunch of numbers that describes its size. So the shape of the creature is also modular, which is what is very nice. It's composed of rectangular pieces, and they are attached to each other by some joints. And these joints can be of different types, okay? They can be a joint that allows just for one type of motions, rotating joints. And these joints can apply forces to the attached rectangles. And so to create a creature, it works like this. So you have a directed graph, like so. Each node represents one piece, and each segment, each edge, represents a connection. Okay? So here, for example, this thing describes this creature because you have a segment which is connected with two instances of the same segment. Okay, so we have the initial segment here, then you apply the rule, so we attach two segments, and then you apply the rule again, so you attach two segments to each new segment, and so on and so forth, and you get this tree-like structure. You have this thing here, for example, let's see, we start with a body segment here. To it we attach three things, so another body segment here, as well as two leg segments, this one and this one, and each leg segment is attached to itself. Okay, so you might say, okay, how do we know where to stop? So actually, each of the node in this tree that describes the creature contains some information about the dimension of the thing, the joint type, so how it is connected to its parent, and the recursion limit is how many times to replicate it for connected to itself. So typically here, for the body segment, we have a recursion limit of 3, which means that these arrows will be executed 3 times to get this body shape, right? Similarly, here we have a recursion level of 1, 2, 3, 4 to get this tree form. And each node also contains a set of neurons or sensors for sensing. Okay? So this is just some, let's say, some way to store some information about what's happening to this specific segment of the creature. So in this model, they use light, so it can perceive some sort of fixed point light which is placed somewhere in the world. Touch, it knows when something is touching the segment, and the current angles of the joining segments. And of course, each node connects to a set of other nodes. And the edges also contain some information. So the edges, the connections between portions, which is the position, so where to place the children node on the parent, and optionally some symmetry. So if you want to place nodes symmetrically, as in this tree, you can build this in the node information. Okay? So what's great is that a very simple graph like this describes perfectly the creature that you need. Okay? And this is one example of what I was saying, is that you need a description which is simple enough that it can be mutated and combined very reliably. Okay, so here, if I want to change the shape of this man, I just need to add a node with some numbers in each segment, and this will automatically be compiled into a creature. Okay, we need this kind of simple description to be able to do mutations and stuff. And so how are the creatures controlled? Well, they have an auxiliary brain, which is completely separated from the creature. And this brain is a neural network. And what the brain does is that it takes as input all the values of the sensors for each of the creature's limbs. And as output, there is one effector, they call them like this, effector neuron, for each joint degree of freedom. Okay? So the brain, all it does is take the information gathered from the limbs and output some movement for each of the joints in the limb. And that's it. Okay, so there is some practicalities that in practice you have also some thinking neurons inside the limbs that they pre-process their data to give into the neural network. And this is useful because the neural network doesn't really know that this leg is very similar to this leg, right? You just get some information about the legs. And so if you do some pre-processing inside the legs, it's easier for them to behave in the same way because they all output some pre-processed information, and then the brain can just use this information to move the leg, but it will not be able to move a leg very differently to one another because it's using chewed up information. So this is some technicality, it's not very important. And so, yeah, so what you do is that now you have your set of numbers, which is the graph, the connection of the graph, the different numbers, dimensions, etc., and the values of the neural network. And so you have this huge set of numbers, I don't know, something like 5,000 or something. And then you just generate random creatures, define a goal through a fitness function. So for example, the creatures need to go forward to get a higher score. You initialize with 300 creatures, score them, keep only the best one, and then reproduce them. How do you reproduce them? You can do it either asexually or sexually. So asexually is just you clone it and apply some mutation. And then sexually, you really go and take the two networks and combine them in some way. And if you do this for long enough, you will get some pretty interesting results. So this is the video that I showed the very first time. So the particularly interesting thing about this model is that because the shape of the creature is determined by this very simple graph, you can allow the graph to also grow during evolution. Okay, so in other words, there are some mutation events, which is add a node in the graph and add some edges in the graph. Okay, this is the explanation. Let's go forward. And so they evolved this creature both to swim, walk, jump, etc. And you get behavior which is kind of reminiscent of what some animal have found, right? Because this is essentially what's happening in nature, but very simplified. So this is what happens during the evolution. And so this is a specific case where we upped the complexity of the agent so much that we reduce the scale to a single element, right? So here there is just a single agent. And again, the emergence of complexity is at the level of the agents itself, what solution it can figure out to solve the problem that it's given. Okay, so this I'll let you look at the video. And then other ways to train the models is with adversarial training. So instead of giving it a fitness function, you still give it a score, but the score depends on how well you do against another agent. And okay, you might say, okay, there is no much difference with what we were doing before, but this is very different because the fitness landscape is very different in this case because it depends on what the other agent is doing. And usually when you train in this way, in an adversarial way, you tend to get much more diverse evolution strategies because you cannot just evolve and kind of stabilize into some ideal solution. Because usually when you kind of stabilize, the adversary can optimize against your found solution. So it will tend to kind of oscillate. Whereas instead, when you just optimize for a fitness function, at some point you find a good solution. And it's very difficult to go away from this solution. There is nothing kind of pushing you away from the solution. Whereas here, if you kind of stabilize on a good solution, it's likely that there will be some weakness that can be exploited and that will force you to reconsider your thing. So adversarial training is one of the tools that you can add to steer your thing towards more open-ended evolution type. Right, so here the goal was to just get the box closer to you and farther away from the opponent. And these are some of the solutions that were found by the creatures. You can see they develop super long arms that can kind of grapple the hoop. It's very interesting what they get. And this is like, I don't remember when it is, but it's, do you know when it was? Like 1990s, probably, maybe even before. And yeah, okay. So these are these Carl Sims creatures. So this is some more modern version, but I think it's less impressive actually, is soft robots. So it's exactly the same thing, but instead of having a graph of hard parts, you just have a soft rubber which is composed of voxels, so just cubes. And these cubes can be of 4 types. So it can be bone, just hard support, tissue, which is soft support, and then you have 2 types of muscles that contract and expand in desynchronized ways. Okay, so one contracts like this, and the other expands when the first one contracts. And so in this example, you have no brain that controls the movement. Each muscle just pulsates according to its thing. And again, you can use these evolutionary algorithms to develop the creatures. And that's the sort of thing you get when you rank them to walk. This is sort of thing you get. So yeah, so they're able to work pretty convincingly despite the fact that there is no brain. So there is no coordination of any of the limbs, just the thing pulsating, but you can still get some walking creatures. Okay, so this is again evolution of complexity at the level of a single agent. And this is the curve of the fitness over time. So as you can see, it evolves by mostly plateauing for a while, and then some mutations accumulate, and usually these mutations are just useless. So they just accumulate, and at some point, all the useless mutations that have accumulated kind of cooperate together, and there is a sudden jump in fitness, and then you stabilize again, and so on and so forth. So again, this is evolutionary algorithms. Is the sort of things you get. Very cool. And yeah, so this, I told you that adversarial learning is a pretty good way to get some complicated behavior. And here's another example of it that is much more recent, I think 2021 or something like that. So the ingredients, the basic ingredients are the same, right? So you have a brain, which is a neural network, which is now more complicated. And in this case, they evolve the agents with reinforcement learning instead of just a genetic algorithm. So without going into the details, with reinforcement learning, you typically learn faster than a genetic algorithm because instead of doing just a random selection of the best, a random search of the possibility landscape, you do a search which is more directed. So you have some information in what changes will make you get better. Whereas in genetic algorithms, you just change randomly and hope it's better. So in this case, what they did is they trained agent in a hide and seek game. Okay, so you have 2 agents on each team. The first team must hide for a limited amount of time they can hide. And after this limited amount of time is done, the seekers activate, and they just have to find a line of sight with the hiding agents. Okay, so this is at the beginning. They just do random stuff. But as you train them, and you really need to train them for long, like it's on the order of millions of examples or million of tests. And so here you can see some behavior that they develop as they get better. Okay, so they learn that they must block the doors to avoid the seeker. Okay, the seeker cannot do much here. So in these cases, they're almost always an optimal solution for the hiders. But as you can see, so here they learn to just block with stones. So the seekers now have learned to use the ramp to enter the seeking. So now in turn, they learn to bring the ramp with them to avoid them using it. So as you can see, this is the adversarial training where one party finds an optimal solution, but then the other party optimizes against this optimal solution. So it becomes suboptimal, and then the other party against improvises, and so on and so forth. So here they use first some simple setups, and as the training goes through, they use harder and harder setups. So here you can see that they make a little shelter, and they can also lock some elements that cannot be moved by the red ones. So here, as you can see, I think this is some exploit that the things begin to find. So it uses the block to kind of, yes. So it surfs with the block by grabbing it on top of it. So this is something which was unexpected, and it manages to kind of use it to surf on top of it. So now the hiders, they learn to defend against the surfing by locking every single block in the zone. And I think at the end there is some video of the glitches that they found. Not in this one. Let me see if I can find it because it's very fun. So yeah, so as I said, this agent training is very good to have some very original solution. And usually it's very good at finding glitches in the simulation. Let me see if I can, yeah. Right, so this is an example here. You can see this one is just pushing the ramp very fast against the wall, and it glitches out and it leaves the field. Okay, that's a valid solution. And since you're exploring this very huge landscape of possibilities, it's very hard to kind of use the design an engine which has 0 glitches. So here you can see another glitch. Yeah. So it uses to glitch and to jump inside to find the seekers. Okay. So this is a kind of crazy behavior that you get when you do adversarial training, because it's very hard to reach a stable position. Okay. So other examples of these very complex agents have been used again by OpenAI to play very complex games such as Dota. So I don't know if you know this game, but it's a cooperation game. It's 5 players. And so they trained a model. I think it was also with self-play. So the model just played against itself. And as with reinforcement learning, it got better and better. And so it got close to the level of professional players. So they claimed it beats professional player, but it's with very specific conditions. You cannot pick all possible heroes, and then you can, and so on and so forth, but still very impressive what you can learn. Okay. So this is kind of more on the machine learning side, less on the Alive side, but still interesting. So if we go back to Alive, there is this project called the Bibits. So it's a project by Leo Kosan, and you can follow, if it's interesting to you, the progress in the YouTube channel. And so this is the best example of an agent-based model for the real purpose of having an artificial life simulation. So what are the Bibits? They are some small creatures which looks like this. And they have a bunch of parameters which determine their size, color, whether they have teeth to kill other Bibits, whether they can digest meat or plants, how fast is their metabolism, if they can move. Okay, so this is an example of the state of a Bibit. So it has some health, some current energy, how long in its growth it is, its age. This is the stomach with what's inside, etc. And they also have, for decision making, again, a very simple neural network. Okay, so you have, here is the brain. So below here is the inputs, the possible inputs. So this is all the senses. So I don't know what they mean, but it's typically the presence of food, the presence of predators, etc., and so on. Here in the middle, you have some hidden neurons. So these neurons have no particular use. They are just used to do some connections and additions of the incoming layers. And here you have the output neurons, which are the actions that the BBIT can take. Okay, so it's the digestion, eating, moving, etc. And so the brain can also evolve again. So you can add neurons in the middle and change the connections if there are inhibitions or excitation and so on and so forth. So you can get complex brains. And they evolve in a world where you have plant-based food. So there is this kind of plant bits that appears regularly. And when a BBIT dies, it leaves behind some meat, and then they can reproduce. I don't know exactly how they reproduce, probably sexually, if they come together and the conditions are right. And so I can show you. I think it will work despite the streaming. So you can just download this. It's actually some sort of a game almost. So it's made with Unity, which is a game engine. And yeah, so this is a perfect example because the agents are very complex, okay? It does not at all arise from simple rules, but it looks like this, okay? So you have this world, this is a bit of food, and this is a BBIT. So if you click on it, you can look at the brain diagram and how it's acting. So you see this, when things light up, it means that it's being activated, okay? So here, yeah, it tells you what it does. So this is acceleration. This is the want to eat function. This is the, I don't know what this is. Anyway, here you can look at its stomach. So as you can see, this is the flow. The flow, I don't know. Yeah. So it's crazy the amounts of parameters that you have in this thing. And this is the DNA. Okay, so the DNA is just a bunch of numbers, as you can see here. And so these control exactly how the BBIT acts, additional to the brain. I think the brain is a separate part of the DNA. And yeah, so you have this world that you seed. I think they can also put some pheromones to guide other BBITs. And so you see these are meat pellets. You can also move them around, etc. And if you wait a while, I think it's still in development, but you will see that slowly, if the conditions are right, if you seed it with a BBIT population which is all vegetarian, which is the case here, if you wait long enough, there will eventually be some predators that emerge. So they evolve some mouth that allows to eat meat first, and they first just scavenge some meat which is left by the dead BBITs. And then after a while, they also evolve teeth to actually damage other BBITs. So I think here we have, yeah, there is this one. I'm not sure what it's doing. But we see there is meat in its stomach. So this one is actually a carnivore. So I think it's still in the stage where it's a scavenger, but then it can evolve predator. And so this very nice ecosystem of things. And this is the perfect example of what I think of when I think of a agent-based life model. So I really suggest to go take a look at this YouTube channel because he explains how it works, and you can see how much the simulation has evolved over the years. So this is an ongoing project. Then a few other things to mention, yeah, real quick. So this one I will mention quickly. So swimbots is another thing which is very similar to the Carl Sims creatures. So here you have different bots of different shapes that evolved to learn to swim. And okay, they can look for a mate or look for food, essentially two things. Then they can reproduce together. And this is, again, some online simulation that you can run in your browser. This is a fun experiment to do. You just launch it in the morning on your computer, let it run, and come back in the afternoon to see how much it has evolved. So these are kind of things you start with. So it's things that really don't swim very well. You can see here it's aiming for this food bit. You can help it a bit to eat. And over time, you should see that if you let it evolve enough, that they will develop actually to be able to swim quite convincingly and swim also in the direction that they want to go. Because this mouth here points that this thing wants to swim here, but it's obviously not able to do so yet. But if you let it enough, if they don't eat enough, they die. They reproduce only when they meet together. And so over time, naturally, you will get things that swim better and better. Okay. And the last thing, probably that I want to mention is Alien, very quickly because I'm getting late. So Alien stands for Artificial Life Environment. And so it's, again, a particle system, but the particles in these systems can get pretty complex. Okay, so you have a bunch of cells that can connect to other cells with springs, and they can choose the rest length of the spring as well as choose the angles between two connections. And so the cells can connect and form these coherent like group structures. Like you can see these squiggly lines here. And the way the system evolves is that each cell has a specific function that it can perform. So you have a lot of function: construction, digestion, sensor, muscle, scanner, and computation. So the one I will present is just computation because it's a less intuitive one. So the computation has a very small program, so maximum 15 lines of assembler line code. So it's a very simple program. And the input of the program is a token, which can be passed around, and the memories of the cell, so whatever it experienced. And so the most important thing is these tokens. So these tokens are packets of information and energy, and these can be transmitted to neighboring cells. And what happens is a cell executes its function only when a token passes through it. Okay. And aside from that, you also have energy particles which kind of permeate the thing and can be absorbed and emitted. And that's how the cells eat and die, etc. And energy is completely conserved, so you have a closed out system. And so you can, usually what happens is that the system is seeded with some sort of self-replicator. So here you have this machine here, which has been handcrafted to create these small kind of hexagons. So you see it's a factory for these hexagons. And what you see, the blinking, this is the token going through the cells and activating their function. Okay? And if you go on this YouTube channel, it has some crazy simulation where it seeds, it seeds the world with these small bits which self-reproduce, and then it let it evolve for a huge amount of time because everything is parallelized on the GPU. The guy was a NVIDIA engineer, I think, so he's very good at programming things in parallel. And so they let it evolve for a huge amount of time, and it's actually impressive the diversity of things that you get. So here you have the things, so you can see that things evolve and die as it goes through. So it's a very lively system. And then here you can see the kind of creatures that evolve. So they are very complicated. They have a bunch of particles. And so this is another case of a mostly agent-based model. It's still a particle system, but the function of each particle does, it's quite high level, right? It either sees, senses, eats, or computes. But still, you can get these huge ecosystems, which looks really nice. And so this, again, you can run it on your computer if you run Windows, only on Windows. Okay, and to finish, I just want to mention, these are mostly created as games, but they can also act as some alive simulations. So these are, the agents are literal animals, okay? The locomotion is kind of hard-coded. The animal can choose to go forward or backward. It doesn't have to coordinate its limbs, etc. And you have plants, and then you can see the world with some sort of creatures, and then you wait and they evolve. And this is really the end point of the agent-based simulations where almost everything is put by hand except for the behavior of the creatures. So this is, again, a game that is in development. I encourage you to go and see some YouTube videos. I haven't much to say about it except that it's kind of the far end of the agent-based model. And here I have some more links in case you want to look at more of these kind of systems. And I will probably add some more links as things come into mind. And I think that's pretty much it for today. So take an eye out for the website. I'm not yet sure if there is course next week. I'll see if I do some kind of wrap-up course of what we've seen. Probably lasts only 1 hour. But keep an eye out on the website. I will update it by Sunday probably to say if there is a course. Okay. See you either in 1 week or in 2 weeks. Hopla.